And finally, welcome everybody to this new session of the PRIMO Talks. And different session with respect to the other. We had to switch platform for some inconveniences. Here we are. And today's speaker is my friend and colleague Simone Rebegoldi from University of Florence. Simone got his PhD at the University of Ferrara now, I think, 4 or 5 years ago. Then he was a postdoc there and at the University of Modena and Reggio Emilia, and he moved as a researcher in Florence last year. And he will today present us a work he has been doing lately, I guess, with colleagues both in Florence and outside Florence. So please, Simone, stage is yours, and good talk.
Thank you very much, Marco. And first of all, I would like to thank the entire PRIMO Group Association for inviting me to this event. So, as Marco was saying, this is a joint work with my colleagues from the University of Florence, so Stefania Bellavia and Benedetta Morini, and also Natasha Kresic from the University of Novi Sad. So in this talk, I will present a new first order trust region method where both function and gradient will be computed in an approximate way, so in an inexact way. And the idea is to provide sort of adaptive technique for computing sample sizes in stochastic gradient methods. So this will be the main message of the talk. So let me start by introducing the problem that we are considering. So we are minimizing the finite sum of n functions of phi I, where phi I will be a continuously differentiable function. So of course, several problems in machine learning can be cast in this form. Of course, binary and multinomial classification, as well as data fitting and sample average approximations are among these applications. And of course, we are also thinking about applications where neural networks are involved in the definition of the functions phi I. And of course, when neural networks are involved, the function phi I will be non-convex, as neural networks are, of course, extremely nonlinear. So we would like to stay in a non-convex setting. And of course, in these kind of applications, n will be really large. So the idea is that both the function and the gradient are quite expensive to evaluate and to compute at each iteration. So this is why we look for stochastic versions of deterministic, very well-known deterministic algorithms. So here I just recall, of course, the most classical approach for solving these problems in a stochastic manner. So the stochastic gradient descent, as most of you know, consists in an iterative process where, starting from an initial guess x0, the next iterate is computed as xk minus a learning rate or step size times an approximation of the full gradient. So the stochastic gradient in the case of subsampling will be of this form here. So here we think of sampling the set of indices from 1 to n. And so we will have a subsample I and k of cardinality nk. And then we will approximate the gradient by averaging over the sample set and averaging, of course, using nk instead of n. If nk is equal to 1, then we get the really standard SGD method with just one single gradient per iteration. So we pick randomly and uniformly one index, and then we compute the gradient with respect to that single index. Otherwise, we will have a sample set where the cardinality is, of course, bigger than 1, and so we will have more indices. We will have a mini batch, and so we call this mini batch SGD. One of the main issues with this with this effective tool is that, of course, you have to choose the learning rate has to be chosen in a very careful manner, and in particular, the optimal alpha, the optimal learning rate is problem dependent. So, of course, even if we do a very standard binary classification, as in this example that I reported here, and we tune the parameter, of course, the parameter will be different from one dataset to the other, because, of course, this optimal learning rate is related to the Lipschitz constant of the function, and the Lipschitz constant, of course, will be different from one problem to the other. So, of course, this is one problem, and the other problem is, of course, is that you can pick the learning rate sufficiently small in order to make the average of the norm of the gradient sufficiently small, arbitrarily small. But the smaller the learning rate is, the slower the convergence rate will be. So these are the two main issues, of course, of the stochastic gradient method. So there are many techniques to overcome these limitations. So there are many different approaches in the literature. So one of the most popular ones is to try reducing the variance of these methods. So we have a GK, which is the approximation of the full gradient, which of course will have a large variance in a stochastic setting. So in SGD, we know that if we compute the gradient of one single phi I, then the variance will be really large. And so this is why SGD may converge slowly or may take a very long, it will stay in a neighborhood of the minimum point, but always, oscillating somehow. So the idea is to look for techniques that reduce the variance, so reduce distance from the gradient, the stochastic gradient, to the full gradient. And so this is the main idea behind the well-known stochastic variance reduction gradient algorithm. Here we basically need to compute every m iterations, we need a full gradient. So every m iterations, we compute a full gradient of fn at a certain point x0. And then for the next m iterations, we compute an iterate which requires the computation of a single gradient phi I, but the stochastic approximation would be something a little bit different when we combine the full gradient with the gradient computed with respect to a single index at the current iteration. So this is a way which we can try reducing the variance. Of course, other methods, very popular methods, are Sarah, Saga, and also Adam, for instance. So this is one approach. The other way is to somehow define hybrid deterministic stochastic methods where the sample size of the gradient is increased at a certain rate, iteration by iteration. So the idea in one very well-known paper by Friedlander and Schmidt is to essentially increase mk at a geometric rate. So you multiply mk by a certain factor, and so in this way, after a certain number of iterations, you will reach the full sample size, and you will obtain nice results about the convergence, and so on and so forth. But of course, the idea here is that after a sufficiently large number of iterations, we will have achieved the full evaluation of the full gradient, which of course is expensive. So these are the two approaches that I won't follow. I won't look at in this talk. There's another how can I say? There's another way of looking at things in the literature, and essentially one alternative idea to the previous ones is to consider the so-called globalization strategies, such as line searches and trust region approaches, and define a stochastic version of or inexact versions of these line search or trust regions approaches. So the idea is to essentially look for variants of the SGD method, which relies on inexact line searches or inexact trust region or stochastic trust region approaches. So there are quite a few number of papers on this idea, essentially from Scheinberg and other authors, also from the group, my group in Florence. So yeah, the idea here is to rely on these globalization strategies for selecting the step length. So we will mimic traditional step acceptance rules using stochastic estimates of both function and gradient. So the purpose here is to overcome somehow the dependence on the step length from the Lipschitz constant of the gradient, which is one of the main issues of SGD. The price to pay in some of these methods is that you require that the functions and the gradients are computed with sufficient accuracy in probability. So this is the drawback, as I'm going to show you in the next slide. So here I'm reporting of the one of the recent algorithms that were considered in these papers from Scheinberg and the other authors. This is called STORM, and this is essentially an example of what I was telling you before following the main idea that I was trying to explain you before. So this is essentially a first order thrust region method where both function and gradient are computed approximately. So at the first step, we consider a model of the function at the current iterate xk, which is a linear model. So you have a linear model around the current iterate on the ball of radius delta k. So delta k is our thrust region radius, xk is the current iterate, gk will be a stochastic gradient, say, computed by subsampling. Okay, so mk is this linear model. Then what you do is that you compute your step by minimizing the model over the ball. And of course, since the model is linear, then this minimization problem is trivial, and what you get is the gradient, the stochastic gradient gk times delta k over the norm. So you have essentially a stochastic gradient step where the learning grade is an adaptive learning grade, because you have delta k, which of course is available at each iteration, divided by the norm of gk. So this is not something which is fixed a priori. It's something that you compute adaptively, iteration per iteration. Then the trust region acceptance criterion comes, and the idea is to, of course, look for a certain criterion to be satisfied, but this criterion will be considered in an exact manner. So here you have the traditional acceptance criterion of trust region methods, where you have the ratio of the actual reduction of the function over the predicted reduction. But this fk0 and fks will be estimates of the full function at the iterates xk and xk plus sk. At the denominator, we have the same for the model, so we will have the predicted reduction of the model. But mk, of course, contains gk, which is itself inexact, stochastic. So you have the ratio of trust region method computed inexactly. And you look if this ratio is bigger than a certain constant n1. And there's this additional condition which essentially links the norm of g with the trust region radius. This is needed in a stochastic setting for this method. So if both these two conditions are accepted, then you update both iterate and the trust region radius by enlarging them, by enlarging the trust region. Otherwise, you freeze iterates and the radius, and you reduce the radius by the same factor gamma. So this is an idea for providing a stochastic version of traditional deterministic methods. And of course, as I was saying, the price to pay and the drawback, in our opinion, is that you need the function and the gradient to be computed in a sufficiently accurate manner. So in probabilistic terms, this means that the probability of certain events should be bigger than constants alpha and beta, where alpha and beta are in the interval 0, 1. So this first event here asks that for a sufficient accuracy in the gradient, essentially. So here we are asking that the gradient of the stochastic gradient is distant from the full gradient, and the distance can be bounded essentially by something proportional to the trust region radius. So, of course, this trust region in a stochastic setting is thought to be convergent to zero, and so for large k, this essentially requires that this distance is going to zero essentially. So we want that this probability is larger than alpha, and the same applies for the function. So here we're essentially requiring that the distance from the real function and the approximated one is smaller than something proportional to the square of the trust region radius. So this is really nice because it allows to obtain very good results in probability. So you can prove that the limit of the norm of the gradient is convergent to zero in probability. But of course, the drawback is that while you have these good, nice results in theory, then in practice, what do these conditions say? Well, they say that the sample size required to compute the function and the gradient as well should be bigger than a certain, a certain threshold, and this threshold will depend on the square, will depend on 1 over the square of the trust region radius. So as I was saying, this trust region radius is converging to zero in a stochastic setting. So this inequality says that for sufficiently large k, you will have here something really, really big, and m essentially will be close, if not equal to n, so the maximum sample size. So these conditions in probability really are telling you that you should somehow you're really close to the maximum sample size, and so you're not you have an algorithm which is in Excel, but in practice requires a really high computational effort for computing gradient and function. So our group, so essentially Stefania, Benedetta, and Natasha, started from this point. And so we were looking for somehow a modification, a variant of this algorithm, of this storm algorithm, where instead of requiring the accuracy and probability for the evaluation of the function, we look for an adaptive technique, a new adaptive technique, which does not require this assumption in probability. So the idea is to propose a new stochastic first-order trust region method similar to the storm algorithm that I showed you before, where the trust region model and acceptor rule both employ function and gradient estimates as in the storm. However, the function sample size, so the sample size needed for function approximations, will be computed in a dynamic way using a deterministic rule. So the idea is to look for a different way for computing the function sample size and thus the gradient sample size. And then we will require probabilistic accuracy for the gradient estimates, but only when the full function sample size is reached. So the idea is to let the gradient sample size be whatever you want, and compute the function sample size in a dynamic way, and then impose the probabilistic accuracy only at when we have reached the full accuracy for the function. So the idea is to delay as far as needed the use of full function sample size. So we delay the use of the full precision and the adoption of the probabilistic accuracy. So we delay this phase, and at the same time, we would like to have a method which doesn't reach this full evaluation, and at the same time provides good reconstructions with good approximations of what we want to achieve. So this is the idea. So how do we compute the sample size, the function sample size in our method? Well, the main ingredient is the application of the so-called inexact restoration method. So this tool has been proposed in a paper, I think I've reported here, yes. This is a paper by Martinez Pilotta from on the Journal Optimization Theory and Applications. So it is not a recent paper, and it is not strictly related to stochastic methods. It is actually a tool proposed for constraint optimization. And the idea is to define a procedure which is useful for problems where you don't need to impose feasibility, to enforce feasibility at each iteration. So the idea is to improve the feasibility to the constraint and optimality in separate procedures. So you will generate a sequence of iterates for your constraint optimization problem, where the iterates are not supposed to satisfy in a precise way the constraint, but the iterates are both improving feasibility and optimality as the iteration goes. So the idea can be very generally and very vaguely summarized in this picture that I'm showing you here. So think of having a minimization problem, which is completely unrelated to the stochastic setting and to the problem that I was the finite sum minimization problem that I was considering before. So think of having a general minimization problem with a certain constraints, say h smaller than 0. And so the idea is to generate a sequence of xk, where at each iteration you first look for a way of improving feasibility. So you do a first step. There's a first phase called restoration phase, where you only look for minimizing the feasibility. So you will reach a point here which of course can be feasible or can be very close to being feasible, but you can see that you have somehow gone far away from the minimum point. So you are actually worsening the optimality. Then you have a second phase called the optimality phase, where you actually look for improving the optimality with respect to the minimization problem, in spite of the constraint of feasibility. So at the end, you will have a second iterate xk plus 1, where you have both improved feasibility and optimality, because here you will reach a point where you are closer to the minimum point. You still are not feasible, but the level of feasibility is better, has improved with respect to the previous iterate, because you are closer to the constraint. So the idea is that in the limit, this procedure will give you a limit point which is feasible, and it is a solution of the minimization problem. So this is the general idea of the inexact restoration method, without going into the details, because now we want to apply this technique to our problem. So we have the finite sum minimization problem, and we would like to have an adaptive technique for computing the sample size for function evaluations. So the idea is to apply this inexact restoration method to dynamically select the function sample size. And so one way to do this is to rewrite the minimization problem in this way. So here we just say, okay, the problem that we are considering can be reformulated as the minimization of Fm, where Fm is the finite sum over a certain set of m elements, where m should be constrained by this constraint here. So m should be equal to n. So here we are just trivially rewriting the same problem by imposing the constraint m equal to n. So once we have that, we have a constraint. So we have a minimization problem with a constraint on the sample size. Okay, so now the idea is to apply the inexact restoration rule for this constraint here, for the constraint m equal to n. And so in order to do so, we need somehow a function which measures the level of infeasibility with respect to the constraint m equal to n. And so this function essentially should be positive for m equal to 1, and then should decrease as the sample size increase. Okay, so the idea is that h will be smaller when the sample size is bigger. And so h will be in particular equal to n, will be equal to 0, sorry, at m equal to n. So one example is to simply consider h as the function n minus m over n. Okay, so this is the idea. We have a measure of the level of infeasibility. We also introduced this function here, psi, which combines, which is essentially a translation in mathematic terms of the idea that I showed you before. So we combine in a separate way the two aspects, optimality and feasibility. We have a convex combination of the function that we would like to minimize, or an approximation of the function we would like to minimize, with the level of infeasibility, which is represented by h, and the parameter of this combination will be theta. So this is the in-excel restoration method applied to our problem. Summarized. So we have these two phases: the restoration phase and the optimality phase. In the first phase, the idea is to look for, so we have two steps. In the first step, we look for a sample size, which we call n tilde, such that the level of infeasibility is reduced by a factor r, where r is something between 0 and 1. So here, essentially, we are saying we would like n tilde to be reduced in a geometric manner. Okay, so n tilde is the sample size that we will have in the hybrid methods that I was talking about before, where the sample size is enlarged in a geometric manner. Okay, so we have n tilde, and in principle, this could be our new sample size. But the idea now is to take a sample size which is smaller than this n tilde. So this nt will be our actual sample size, and the goal is to actually reduce the computational burden for the iteration k. So once we have this, then I will show you how essentially we do this in practice. And once we have the sample size, we compute the trial point using a certain model, which will be the first order trust region model of the function f. And then we consider the predicted and actual reduction as these two quantities. This is a modification of the standard prediction and actual reduction quantities, because we don't have the simple differences between the function and the model, but we have a combination between the function and the level of infeasibility. So, for instance, the predicted reduction is given by the convex combination of the predicted reduction for the function plus the predicted reduction for the infeasibility level. And then the same applies for the actual reduction, where the difference here is done for the function psi, for the merit function psi, and not the actual function f. Then we accept the trial point or not according to this condition here, which is essentially the trust region acceptance criterion. Then, of course, this is the first ingredient. The second ingredient is the trust region approach. As we've seen before, we consider a linear model of the function, we minimize it, and so we will have a trial point of this form while the linear rate is adaptive. And the stochastic gradient, in our analysis, can be any approximation of the gradient, full gradient. For instance, we can think of this gradient here as the subsample gradient, where the sample size, the sample size of the gradient will be smaller than the sample size for the function. So this is the proposed algorithm. We called it the stochastic in-excel restoration trust region algorithm. And so this is really complicated because we wanted to be really precise in the notations, but the idea is actually really simple. So at the beginning, we choose the initial guess, x0, the initial sample size. This is the penalty parameter for the in-excel restoration approach. And then we have some parameters which are the trust region line search parameters, essentially. So these are the parameters that are also needed in a deterministic setting. So at every iteration, we first compute the n tilde sample size that I was talking about. So you look for essentially a geometric decrease of the infeasibility measure. And then you look for an actual sample size, nt, such that this condition is satisfied. So here we are involving the value of infeasibility at the sample size and tilde, and the trust region itself. So basically, we are choosing the sample size in taking into account the information on the current trust region radius. So the idea is that this condition also allows the decrease of the sample size from one iteration to the other, so that the computational effort is somehow reduced in at least in the very first iterations. Okay, so the goal again is to run this algorithm, but stop it really before the full function precision is reached. So we would like to have something which reduces the sample size in the very first iteration way before the maximum sample size is reached. And then all the following steps really are the essentially the trust region steps of the trust region method. So you will compute the penalty term in a very complicated way, but the idea is that you need to impose this condition here. And then you will check if these two conditions are satisfied. So these conditions are borrowed from somehow borrowed from the STORM algorithm. This one in particular is borrowed from the STORM algorithm. This other one is essentially the trust region acceptance criterion, where we are also including information about the level of infeasibility. And so we, of course, we accept or reject the trial point according to these two conditions here. So this is the method, and of course, one is interested in some theoretical results, essentially about the direction where this method is going. In particular, is the sample size increasing as the iteration proceeds? The answer is yes. The idea is that we can show under suitable assumptions that for sufficiently large k, the sample size, the function sample size, will be equal to the maximum sample size. So we are converging. We are going into a setting where the function will be computed exactly. So some assumptions are needed for this. In particular, we need that the function is bounded from below and above. We need that the gradients are Lipschitz continuous, and that somehow the gradient, the distance between the current gradient and the gradient f computed with the function sample size is bounded by a certain constant. So if we use subsampling, this condition is satisfied. But what we can prove is that the trust region here is going to 0, and then nk will be equal to n for sufficiently large iterations. And here I just reported some really sparse details on how we can prove it. The idea is to define a Lyapunov type function where you combine informations on the function, so on the optimality, and information on the trust region radius delta. So you define a function which combines the two aspects, and then you can prove that the function, this Lyapunov function, is decreasing. So with this trust region approach, of course, the full function is not decreasing, but we can prove that this one decreases with this sufficient decrease condition reported here. And so from this, we can prove that delta k is going to 0, and since the sample size is related to the trust region radius, the sample size will be equal to n eventually for sufficiently large k. Okay, so once we are there, so once we will have achieved the full sample, we can prove results in probability, but this can be done in the same way as done for the STORM algorithm in the papers by Scheinberg and other authors. So you can prove that so once you achieve the full maximum sample size, if the model is sufficiently, if the model for the function is sufficiently accurate in probability, then you can prove that the limit of the gradient is 0 in probability. So the probability of this event will be equal to 1. And so again, here we haven't how can I say it? We haven't said anything more than what was said for the storm algorithm. So this result is taken from that paper. We have convergence in probability. This is good. What we have achieved somehow is that we don't need this assumption before the full precision in function is achieved. So we do not need this assumption on the gradient before the full sample size for the function is achieved. And so this in practice is an advantage, because it allows us to, we know that our procedure is going in the right direction, but we don't need the probabilistic assumption on the gradient for computing the iterates. And so this is good in practice, as I'm going to show you in these final slides here. So here I'm reporting some simulations, some numerical experience on a non-convex binary classification problem, where we are minimizing the square loss combined with the sigmoid function. So AI and BI are the examples and the labels. This is the sigmoid function, so the loss will be overall non-convex. So this was a way to consider a non-convex version of the traditional logistic regression problem. So we consider some data sets, some really popular data sets for these purposes, and so with different size for the training set, and for the number of features as well. So some details for the computation, for the implementation of the algorithm. So the feasibility measure H is computed in this way. So if you use this H function, then you can see that the n tilde will be computed as essentially in a geometric manner. So you are increasing nk by a factor c, essentially at every iteration. The function sample size it will be computed as n tilde minus something proportional to the trust region radius times a certain parameter mu here. So mu here, of course, needs to be tuned, but we will see that using a reasonable choice of mu, we will have some really good results. Stochastic gradient is computed by subsampling, and we stop the iteration when either the norm of the approximated gradient is smaller than a certain tolerance, or the relative decrease of the function is, again, smaller than a certain epsilon. So the following tables here are, the goal of these tables is to show you that once you have set your parameters of the algorithm, which are still several parameters, but once you have set them, then you will obtain reasonable results for many data sets. So the idea is that the algorithm is not so sensitive to the choice of the parameters. So here, actually, what we did was to fix all the parameters of the algorithms except n tilde. And in particular, here we look at the results, the classification results for our algorithm by varying the n tilde, and in particular the growth factor. So here we increase n tilde by using different factors for the geometric growth. What we can see here we have 3 columns, and the first one is essentially the number of full function and gradient evaluations. The second column is the classification error, and the third one is the number of times that the problem is solved without reaching the full precision in function evaluation. So here we look at how many times the stopping criterion is reached without the function being computed in a full way, in a full manner. So as we can see here, the classification error is quite stable to the choice of the growth factor. And but you can also see that by reducing the growth factor, which means increasing n tilde in a very slow way, we are able to increase the number of times in which the problem is solved using a small function sample size. So the error is stable, but we are reducing the number of times where the full precision is achieved. So this is good. And we did the same, fixing all the parameters and varying only the initial sample size for the function. So this n0 needs of course to be chosen. And so we looked at the effect of the choice of this n0 on the classification error for different data sets. And what we can see here is that what we said before is still true. I mean, the choice of n0, the algorithm is not so sensitive to the choice of n0, but we have to be more careful here. I mean, if for some data sets, if n0 is too small at the beginning, then the classification error will be bigger. And so this means that we need essentially here, if you look at the NIST data set, you see that the classification error is really bigger. And so here you have to be, so this of course only for this data set, but of course this can happen also in other situations. So you have to be careful on the choice of the initial sample size, essentially. So here I'm just reporting an example where the function sample size actually decreases from one iteration to the other. So here we have the cardinality of the sample size versus the number of iteration for two different settings of the parameters mu, which is involved in the computation of the actual sample size. So if mu is chosen in a good manner, then we can reduce the function sample size at the very first iteration. Then, of course, it will follow a geometric increase, a geometric pattern in the growth. Finally, we wanted to show also a comparison of our algorithm with another trust region, a stochastic trust region approach that has been proposed recently. So this approach is called the TRISH, which stands for Trust Region-ish Algorithm. And as the title explains, the idea is to somehow do a trust region step under a certain hypothesis. In particular, the trust region step will be made only if the norm of the stochastic gradient is in the interval that you see here. Otherwise, you will perform a stochastic gradient descent step. So you see that here you have all these alpha and gamma parameters. So also here you have a certain number of parameters. But the idea here is that the parameters are very similar to the one that you need to choose in the SGD method. While in our approach, we have, of course, many parameters, which are, however, characterize a trust region approach. So somehow, you know that in a deterministic setting, these parameters can be chosen in a reasonable way, and then you will have good results for many data sets. So the idea is to show that this is also the case when in a stochastic manner, in a stochastic setting. And then you have a good approach also if compared to stochastic gradient descent method like. So in this last slide, what I'm showing you is the decrease of the testing loss for two different data sets with respect to the number of epochs, essentially. So the dotted line is the line of our algorithm, while the solid lines are several runs of the TRISH algorithm using different learning rates. So you can see that, of course, the optimal learning rate for one data set and the other one is different for TRISH, while our algorithm performs in a good manner for both the A9A and the H2 data sets. So the idea is that we have a proposed algorithm where you have many parameters, but these parameters are the ones of globalization strategies, so the ones of trust region approaches and line search approaches. So you can choose them somehow in a reasonable way, and you can have results which are good independently of the data sets which are considered. So to conclude, we have proposed our first order trust region method with function and gradient estimates. We have proved that this method eventually reaches full precision for evaluating the function, the objective function. And the preliminary numerical tests are good because they show that the method is stable with respect to the parameters. There are many parameters, of course, but the method is more or less stable to these parameters. And so the idea is to apply this method and delay the use of the full sample size as much as we can. The future work, so future activity will concern the application of this method to neural networks. So it will be good to see an application of the method to concrete real-life problems. And another idea then we would like to explore is to consider the same strategy for computing the sample size without the need of achieving full precision for the function. So if we don't achieve this full precision, what happens? What can we prove about the algorithm? This is one idea for future activities. So thank you very much for the attention, and any question or curiosities I would like to know.
Thanks a lot, Simone. Very nice talk. And so I think if anyone wants to ask a question to Simone, you can raise your hand using the Google Meet tool, or write in the chat, or unmute yourself and ask your question. And if there is no prompt question, maybe I can start with my curiosities. Simone, if you're okay with that.
Sure.
First thing first, just a clarification for me. So the function sample size and gradient sample size are different for you. So even if you don't reach the full function sample size, you have so even if you reach the full sample size for the function, doesn't mean that you have full sample size for gradient evaluation. Is that true?
Yeah.
And maybe I missed it. And how do you in general choose the gradient sample size with respect to the function sample size? So is there a rule you follow, or?
Okay, so before the maximal function sample size is achieved, is reached, in theory, so for the theoretical results, you don't need any particular rule for computing the gradient. So you only need that the norm of the gradient minus the full gradient or something like that is bounded from above. So this is the only assumption. And so you can compute it essentially however you want. In our tests, we chose the gradient sample size smaller than the function sample size. So once we have computed the function sample size, we take the n
a portion of that.
Yeah, exactly a fraction of the function sample size.
Okay.
So,
So
this
clarifies my doubt. So now I can proceed with my question.
Sure.
So first of all, one curiosity. Okay, I've seen that in practice, in many cases, the algorithm does not reach the full function sample size. And as you have said, in future work, you would like to see if from the theoretical point of view, you can work on a modification which allows you to avoid that.
Yeah.
But I have a curiosity regarding on the way you presented the inexact restoration framework, in saying, okay, I want to have a function h, and you took the function n minus n divided by n, and say, okay, I want it at each step to be to decrease geometrically. Which means that since your function more or less is linear in M, you increase your sample size geometrically.
Yeah, by a factor.
So what would happen? And have you tried alternative formulation of H, in which, for example, the value of H doesn't go linearly to 0, but maybe it goes slowly. So in order to avoid a geometric increase in the function sample, and maybe slowing down that increase.
Yeah,
have you tried?
No, we haven't tried, at least for this paper. But this is a good idea. I'm not sure if, because in theory you don't have you don't speak about geometric growth. You have this condition here, but what you're saying here is that the level of feasibility is decreasing by factor. So I'm not sure how, if you can have other functions which satisfies the properties shown before, but I guess that more or less, yeah, we haven't tried, but I'm not sure at this point of which functions H could satisfy, these conditions without requiring the growth pattern, let's say.
Yeah.
But it's a good idea. I mean, it's a very good idea. I'm not sure if there are other, since these in-excel restoration techniques has been applied other times in other papers by Natasha. I don't know if maybe other choices have been considered, but
Yeah,
it's a good idea.
I remember some other talks by her in
Mhm.
which she said, yeah, of course you can make the simple choice of the
Mm.
linear decreasing
Yeah,
function, which
yeah.
it's easy, but it was just a curiosity if
Mhm.
something different could be done.
Mhm.
But thanks for the answer.
Yeah,
I have
yeah.
another one, but I think Daniela raised his hand, so Daniela, feel free to unmute yourself and
Okay.
ask your question
Thank
to
you.
Simone.
Thank you.
Nice
Simone,
beach screen behind
yes,
you.
a place where I would like to be now.
Yeah,
Okay.
every one of us, I guess.
Okay.
me,
So,
me too.
maybe this is a stupid question, because I must say that when you were discussing about the techniques for reducing the variance in the gradient, and then you were also introducing the inexact restoration technique, I missed the connection. And now I'm using my smartphone, okay, in hotspot, because I have no more connection.
Oh.
So maybe you said that, but I didn't understand if with this technique you are able to reduce the variance of your gradient, because usually in that case you get a very strong practical improvement, at least practical improvement of the speed of convergence. So I didn't understand this, but probably it's my fault because I missed at least 5 slides. I must confess
I
that.
see. I see. No, well, in fact, it is the opposite. I mean, I had this. Sorry, my phone is ringing. So I'm hoping someone is answering. No. Okay. Great.
That's the problem when you are at home.
Yeah, exactly. Because both phones, both the mobile and the fixed one, were here. So that was the problem. So as I was saying, so it is actually the other way around, meaning that this slide, I added this slide to say, okay, there are many approaches in the literature to overcome certain limitations of SGD. The one is reducing the variance of the gradient, but then I said, no, I'm going in
and I missed this one. Okay,
direction.
sorry.
Also, no, but it's okay. I mean, because also GK can be, we don't have really strict assumptions on GK before reaching the function sample size. So GK can be essentially really a standard subsample gradient, and but we didn't consider, variance reduction techniques in theoretical results.
I had this curiosity because in general, when you increase the sample and you are actually increasing it, you have the possibility of reducing the variance by using this trick. Okay, yes, but in any case, I missed these slides, so I was not able to give an answer to this question by myself, listening at the remaining part of the talk. So I apologize for that. Anyway, thanks a lot for the answer.
You're welcome.
Yeah, actually, my other curiosity was exactly about this, because I think more or less the answer was given in the sense that if you increase your sample size, automatically you are reducing variance. So it's another way of reducing variance of your gradient somehow. But nevertheless, are you planning or of maybe trying at least some of those methods, especially in the first stages of the algorithm in which your sample size is small?
It would be nice to see if you can have some results. I mean, in the way you can have them for SGD or the stochastic variance reduction method. Using these techniques. It would be nice to keep the sample size Yeah, but then it's a challenge, I think, because then you have an acceptance criterion, but you are using an approximate estimate of the function. So what are you reducing actually? You are reducing something, but not the function. So maybe you will have results, but not on the full function. Maybe on the merit function. I don't know. We should look at that.
Yeah, I think it's tricky because
for sure.
your model, I think, needs to be as close as possible as the original model. So you need the gradient of the subsampled function somehow. So as soon as you plug in some variance reduction technique, you lose that because your gradient will be unbiased, but at each iteration it is not the gradient of the subsampled function you are considering. So that could be ruin at least the convergence of the trust region scheme because you have misleading information. But maybe it could be worth a try. I don't know. From practical point of view, it could be beneficial, but of course, theory needs to work as well.
Yeah.
So thank you, Simone, for this other clarification. So, are there any other questions for Simone? Feel free. Don't be shy. Simone is fully available to answer all your curiosities. Okay, looks like there are no other questions for you, Simone, today. So I think I can set you free for this afternoon. You have done enough. It's, I think, 6 p.m. Yes, past 6 p.m. So maybe you deserve some rest. So thanks a lot again for accepting our invitation and to all the attendees for attending today's session. Before closing this, just wanted to make an announcement. So in the previous month, it happened that we talked about a workshop we were planning to do in Bologna. And because we got funds from the Department of Mathematics and we are planning it, now we are ready to tell you that we fixed some dates and we are planning to have a PRIMO workshop in Bologna on 11th to 13th of October 2021, so 4 months from now. And we already have a website, which I'm posting in the chat for you now. Registration to the workshop is already open because we are trying to understand which is the number of possible participants. The number will be limited because there will be, of course, some limitation for the COVID-19 situation and also from the budget point of view, because we aim to offer the participant lunches and coffee breaks, at least. Not the most finest food, maybe, but still something. So I think we will share the news also with the PRIMO mailing list and some other mailing lists in order to have the most contacts as possible. And I hope if you're interested, you will start register. And we will potentially open next month the possibility of submitting an abstract for presentations, because of course that's the idea. The main, it's a workshop, so we need also people to present their work, and we hope young people are willing to do that. So this was the announcement, and I think I didn't forget anything, and I asked my fellow PRIMO members to correct me if I was wrong. And if not, thanks again, Simone, and we will see you all, I think, in a couple of weeks with the next session of PRIMO Talks.
Grazie Simone, grazie a tutti e arrivederci.